Thank you. So, well, it's a pleasure to open this only session on quantum foundations. So I'll be talking about, how to self-test all entangled pure states in quantum networks. So, I'm Ivan Supic, and I work in University Sorbonne in Leipzig in Paris. And, my co-authors on these papers are Joe Bowles, Marc-Olivier Renou, Antonio Acin, and Matty Hoban. So Marc-Olivier, Tony, and Matty are also here, so you could also ask them if you have some questions or interest. I'll start with something that is probably very familiar to everyone, but just to make a nice introduction. So this is a concept of non-local games in which, as probably you know, we have like two players, Alice and Bob. They are getting some classical questions, X and Y, and they are supposed to return some classical answer, A and B. And we could quantify their success in these non-local games based on resources they use. And they cannot communicate. So there is something that we call classical bound. That is the best bound that can be achieved if they are using only classical resources, so deterministic local strategies. But then they could actually use quantum resources, so they could share a quantum state, rho, and perform some measurement depending on input and output, and use the measurement outputs as answers. So this quantum strategy, particular quantum strategy that they use, it can get them score higher than the classical bound if, so it's a necessary but not sufficient, if the state they share is entangled, and if measurement of Alice are incompatible, so meaning non-jointly measurable, and also measurements of Bob, the same. So if we do supremum over all possible quantum strategies, like we get something that we call quantum bound, that is the best possible score that quantum players can achieve in game like this. Okay, so from the fact that entanglement and incompatibility are necessary conditions for success in these non-local games, we know that if we observe score in the game higher than the classical bound, that this can serve as a witness of entanglement and incompatibility. And this witness is we don't make any assumptions about the devices used, like it's simply from the success in the non-local game, or if you want more from the probability distribution. So like this type of black box certification of entanglement we call device independence. So this is one concept. And now, we could ask if we can get some stronger conclusions if we actually reach this bound, that is this quantum bound. It is the best score that could be achieved with quantum resources. So since any score higher than classical witness is entanglement, the question would be, could it be that we can know something more if we reach this quantum bound? So the answer for this, in the case of well-known CHSH game, was given like more than 20 years in the works of Cyrelson and Popescu and Roerich that proved that this optimal score in CHSH game could be achieved only if maximal entangled state pair of qubits is shared between players. And this is related to a mathematical concept of rigidity, where we are determining some object from much less information than we would expect to. So here it is just like the maximal score in CHSH game determines like the form of the state used. So, the concept of, and in this case, you would say that this maximal score in CHSH game self-tests the maximal entangled pair of qubits. So the concept of self-testing was introduced by Myers and Yao in 2004, and it says that some state psi n that we call target state or reference state, it can be self-tested if there exists quantum correlations such that for any quantum realization of them, we can find n local quantum map that extract a form of the state like this. So we are extracting coherent superposition of our target state and its complex conjugate. And we explain here why we need these local maps and why we have this complex conjugation that we cannot avoid. That is because we are observing simply correlations, and there is a whole set of transformations that don't change probability distribution. So we could do local changes of basis, or we have some uncorrelated degrees of freedom. So all these transformations are encompassed by these local extraction maps. But furthermore, except for these physical transformations, we also know that if we have a state and measurements and their complex conjugate, they could give us the same probability distribution. So that means somehow that we cannot distinguish if we have just psi or we have this coherent superposition of psi and psi star. meaning that in self-testing, like this is kind of the best, in standard self-testing, this is the best that we can hope for. So well, beyond like this foundational interest, like self-testing is important as a primitive for DI quantum state certification, for verification of computation and delegated computation, for establishing relations between quantum computational complexity classes, for various cryptographic protocols. And then the question is like, since conception of self-testing level, which states could be self-tested? So we had some results that were like partially like general. So we know how to self-test partially entangled pair of qubits, then all qubit pure bipartite entangled state, meaning all bipartite pure entangled state, all qubit graph states, all qubit GHZ states, all decay states. So we had several classes of states, but the question then is, well, is it possible to self-test any possible state? So this task seems complicated because for any particular state or state that has some structure, we need to find the correlations that are self-testing it, and these correlations depend on the form of the state, on some symmetry or something. So if you have arbitrary quantum state without symmetries, like it seems quite difficult to find a way to self-test this state, and our paper is the answer to this problem. So we find a way to self-test all pure entangled states, but we introduce a small change of scenarios. You want to use the tool or resource of quantum networks. So quantum network, we talk about quantum networks in these correlation scenarios. If we don't have just one source distributing like states to all parties, but we have 2 or more sources that are mutually independent. So that means that underlying state, if we assume this network structure, we can see it as a tensor product. So there is some tensor product structure of the underlying state, and this network in correlation scenarios, well, it has used for entanglement swapping, quantum repeaters, quantum internet. It led to the phenomenon of non-locality without inputs. It was used in this proof that quantum theory needs complex numbers. So somehow it's a good tool and useful tool for finding new effects and also for some practical things. But now, like, you could wonder, well, why could we hope that by somehow having this network structure, like, we could get something more? Well, intuitively, we are just allowing our quantum resources to expose a richer correlation structure. Because if we have a network and we have like two, for example, to some party we are is having like states emitted from 2 different sources, like we are allowing also for entangling measurements. So we allow for different for richer correlation structure. So in this case, we change a bit definition and we introduce what it means to self-test some state in a network. So we define network-assisted self-testing that if we have a state n partite, we put it in a network of m parties, that is m is bigger than n, and then if there exists m partite correlations on all parties, such that for any quantum realization of all these correlations, we can find n local maps that extract our state. We say that we have this network-assisted self-testing. So I will not go into all the technical details because, well, if anybody was working on self-testing knows that it's a very meticulous job because you have to be very careful with all the isometries and steps. So I would rather show you like intuition and like structure of our proof and maybe just pinpoint some technical contributions that might be important. So, well, we start there from quantum state tomography that is device dependent, but it is a device dependent primitive for recovering form of quantum state. And interestingly for us, it does not depend on the form of state. For any state of given dimension, we are doing it in the same way. And it's already something good because for self-testing, for us, the problem was that for any different state, we would need to tailor the protocol. So our intuition is here to step by step make tomography process device independent by introducing network. And like in the first step, we want to show equivalence between tomography and something that we call measurement device independent tomography. Then we would go to some network assisted tomography and finally to self-testing. So I go with each step. So in the first step, we want to show equivalence. How can we find equivalence between tomography and this thing that I call measurement device independent tomography? So in tomography, we have a trusted measurement that we apply on untrusted state, while in measurement device independent tomography, we are having trusted quantum states that we call quantum inputs also to the scenario. And here you could see how we could find how we can exchange a characterized measurement with this input is that, well, the correlations on any unknown, like, so here it could be any state, on some measurement that projects on some state psi, we could see it also as if we have our state rho, and then this state psi to which this projector goes, and then we do Bell state measurement and do projection on phi plus, for example. So, like, we see that the characterized measurement could be exchanged with a characterized quantum input and a Bell state measurement. So now in this first part, you might think, okay, but you are going in the wrong direction, because at the beginning, in tomography, you needed just one trusted measurement, but now you need trusted state and the Bell state measurement. But okay, we'll see how it goes. Like, one thing why we do this is because this measurement device independent tomography or self-testing with quantum inputs, we have this proof that shows that in this scenario, with quantum inputs, we can actually self-test any entangled pure state of any local dimension of Hilbert space. Okay, so now we go to this step 2 to see how we can do this network-assisted tomography. So in measurement device independent tomography, we had these quantum inputs. But now so here network comes into game because we have these additional sources, and like these quantum inputs can be prepared for these parties that are holding unknown state that I call main parties. We can add some auxiliary or additional parties that if they apply corresponding measurement on the maximally entangled pair of qubits, they would prepare like these quantum inputs. So, well, this is a simple thing to show. And then, well, the question is, so now I went even more like into, it seems in the wrong direction, because not just that I needed like trusted characterized measurement, but I need characterized measurement and maximally entangled pair of qubits. But there things come to become a bit simpler, because like unlike in the tomography scenario where we have these characterized measurements, we cannot really self-test them when they act on arbitrary state. But this thing here, so maximal entangled state and tomographically complete set of inputs, tomographically complete set of measurements, we can hope to self-test, and we show that we can do it. So the problem is exactly this, what I said. And then, like, well, we do it for qubit case. It's a simple procedure. So if we have a CHSH inequality or CHSH non-local game, so maximal score certifies anti-commuting measurements per party. And then if we make these three CHSH inequalities that are nicely made, that, for example, these auxiliary parties using B0 and B1 in the first, B0 and B2 in second, and B1, B2 in third. So if they're all maximally violated, we know that these measurements B0, B1, B2, measurement observables, are mutually anti-commuting. And hence, we can show if they are anti-commuting that they are isometric to free Pauli observables, and this is something that is tomographically complete. So it is something that helps us solve the problem. So, okay, now we saw these various steps that goes from tomography to like device-independent tomography or self-testing if you want. And like in principle, the recipe to do self-testing would be the following. So we would have some two types of rounds. In some rounds, we would ask auxiliary and main parties to perform measurements that maximally violate this chain CHSH inequality. In this way, we would self-test these maximally entangled states, and more importantly, we would self-test the measurements applied by these auxiliary parties. In some other rounds that we call teleportation round, auxiliary parties would be asked to perform the same measurement, again, like they did in the testing rounds, while the main parties would be asked to perform Bell state measurement. In that way, if they really apply Bell state measurement, like the state that main parties share would be teleported to auxiliary parties, and we already did self-testing of the measurement of the auxiliary parties. So in some sense, we could do the device-independent tomography of that teleported state. So we don't trust Bell state measurements because, like, we need like if they don't apply Bell state measurements, they will teleport some state that would not give that device-independent tomography would not correctly recover. So we would accept only if the correlations that these characterized measurements have on the unknown teleported state are those that we want them to be, because we want to self-test some reference state. Okay, so now this is all nice, and there is this intuition, but we have one problem that I mentioned at the beginning, and that is that we cannot self-test states and measurements perfectly, but we can do it only up to complex conjugation. So if we have some unknown measurement, like, well, this would be like extension of our map that is unitary, it maps it to like ideal state tensors, ideal measurement tensor sum projector plus complex conjugate of the ideal measurement tensor sum projector on the orthogonal subspace. So, well, this would not be a problem, for example, if you want to self-test sigma z and sigma x, but if you want to self-test sigma y, this is a problematic thing, because, like, we don't know if the party is applying sigma y or sigma y star that corresponds basically to flipping outcomes of sigma y measurements. And for that, we needed to prove this technical primitive that we're calling differently in different versions of paper, but we could call it somehow partial tomography or almost tomography lemma. So, and that is that if we have access to some correlations that are modeled like as simply performing measurements that are obtained by performing measurements on an unknown state, and then we have this promise that we get from self-testing that these measurements have exactly this form. So they are partially characterized on this qubit subspace, that they are either ideal measurement or its complex conjugate. And well, if they are tomographically complete on each site. So our lemma says if observed correlations are such that we would see if we have measured our target state with perfect measurements, where our reference state is pure entangled state, then the state giving these correlations must be kind of a mixture of our ideal state and its complex conjugate. So this lemma works importantly only for pure state. It does not work for mixed states, and only for entangled states. Okay, so then like we kind of this is something that we would like to get, because we know that in self-testing we can only recover the state up to this complex conjugation. So like it already gives us what we want. And then like, well, here we have scenarios, network scenarios for our self-testing, and we have different scenarios depending on if we make assumption about network structure or not. So when I say that we make assumption on network structure, it means that we assume that different sources that comprise the network are mutually independent. So in that case, we have one auxiliary party that shares with each of these main parties one maximal entangled pair of qubits and is preparing quantum inputs for them. And then like with Bell state measurements, like we could do the process. However, we don't need that assumption to get our result. If we don't make any assumption about this network structure about network structure and about tensor product structure of the underlying state, we can still do this self-testing, but we need that these auxiliary parties are separated. So like in case of assuming network structure, like we have n+1 parties involved in the protocol, while if you don't make assumption, we have 2n parties. So, well, it's a same scaling at the end. Like, and then, like, if our results are also a bit different depending on whether we make this assumption or not. So, if we make, if we don't make any assumption about network structure, we can find the local map that is mapping the underlying state to exactly what we expect it to get. That is like coherent superposition of target state and its complex conjugate. But if we assume network structure, then actually we can break this coherent superposition, and we can know that the underlying state must have been either ideal state or reference state. So this is of course up to local isometry. So we have this quantum map here. So somehow here, like the assuming network structure allows us to extract more information if you want, because we break the superposition to just two cases. Okay, so well, we answered there in one question that was open for some time about whether or not all pure entangled states can be self-tested. So if people are more interested in things like I put here some open questions that would need probably solution. And for the end, I have just one announcement from one of the co-authors of the paper. Like he's starting a group in École Polytechnique in Paris, and they have a call for a permanent position in quantum computing. So if you are interested, or if you know somebody that is interested, you could meet, you could talk with Marc-Olivier or write to him on this email. So, well, that's all that I wanted to say for today. Thanks for your attention.
Thank you, Ivan, for this nice talk. Any questions?
Hi, Ivan. Thanks for the talk. So you said that the theorem about tomography does not apply to mixed states, right?
No, so tomography applies to all states, but this almost tomography does not apply. So if we have that, we don't have a perfectly characterized measurements, but they are of this form where we don't know if it's our measurement or its complex conjugate, then we cannot actually hope to recover any state with such tomography process, but only pure states.
Okay, so I mean, so you mean to say that, like, we cannot have similar maps like the pure states, like rho and rho star, like a superposition of rho and rho star?
No, but okay, so like in that case, like if the state is mixed, like then like rho and rho star are not necessarily the only ones that can give us this. Because somehow here, if you have this complex conjugation, it corresponds, you can move it to partial transposition. So you could just do the dual thing and move the partial transposition. So it would correspond as if you have a kind of sum of your ideal measurements, but then apply on rho, but then partial transpose over all parties everywhere. And then like these to eliminate somehow like all these elements of the sum, like you need state to be pure, because then partial transpose become negative. But there are entangled states with positive partial transpose.
Hi, I just wanted to clarify about the assumptions. You kind of mentioned that. So but I didn't fully get it. So like, do you need to assume that the state shared by all the parties in your picture, that there's some kind of entanglement structure, that there is no entanglement between parties that don't have an edge between them? So so these edges are a bit like it doesn't represent some graph state or no. It's just that these parties, they want to convince us that they are sharing some entangled state, some pure entangled state among them. And then here, we are not making assumptions that then there are these additional maximally entangled states between each main and auxiliary parties, but we are inferring it through self-testing. So. Yeah, but if there is no edge, do you assume that there's no entangled state between those parties? Yes. So if we have a network structure like this, we assume that there is so this party does not share anything here. But I think in this case, probably it wouldn't change much, because like when we self-test these maximal entangled states, they are uncorrelated with anything else. So if there would be something else, it would be uncorrelated. But it could change robustness.
Hi, thanks for a great talk. So in the first step, do you have to assume anything about dimensionality of the singlet that you use and Bell state measurement? And like, in principle, you don't know the dimension of local subsystem.
We don't know the dimension of the underlying physical state, but then we know the dimension of the state we want to self-test. And in that case, here, also when we are doing tomography, we kind of are doing like if it's qubit, we'll do qubit tomographically complete measurements. And then here, like this maximal entangled state needs to be in the same dimension. So if the state we want to self-test is a qubit, it needs to be maximal entangled pair of qubits. If it's higher, so it follows the.
Yes, thanks for the talk and congratulations for the nice results.
Thank you.
Just a question about what happens for states of higher dimension than qubits? Like, what is the next ingredient you need for that?
So, okay, somehow the general idea is the same, right? Like, we just do the same things. Well, the problem is then that if it's higher dimension, for example, if it's Q-treats, we would need to self-test here maximum entangled pair of Q-treats and tomographically complete set of measurements there. But we are doing this by somehow self-testing like a bit more than we need, like because that's what we know how to do. For example, we would embed it in larger dimension that corresponds to tensor product of 2 qubits, and then I would do I would do parallel self-testing of many pairs of qubits, and then I would embed it there, and I would do that. So like for that case, for higher dimensions, then in this part it becomes much more technical because we need to do this parallel self-testing.
Okay, so thank you, Ivan. So we need to stop here because we need to let people go to another session. So thanks again.